A special application of graphing multiple inequalities is called linear programming. In linear programming, we often want to find a maximum or minimum value for some quantity, and that quantity is going to be given by a set of constraints. Constraints is just going to be a fancy word for the inequalities that we graph. A lot of times when we talk about real-world problems, the constraint is that our graph ends up in quadrant 1. When we graph a set of inequalities, we want to look for the region where all the shadings overlap. This is going to have a special name. It's going to be called the feasible region. It's really just your shaded region where the shadings overlap. When we're trying to maximize or minimize a quantity, we're going to be given something called an objective function. The objective function is usually if we're trying to find a maximum profit. You own a business, you want to find out what's the most amount of money you can make based off a set of constraints. But we're sometimes trying to find a minimum cost. What's the minimum amount of money that I need to put into my company so that I can have goods to sell? When we have a graph in quadrant 1, a lot of times we're going to end up with some sort of polygon. Sometimes it's a triangle, sometimes it's a quadrilateral, it can be a pentagon or a hexagon, but the ones we're going to see are going to tend to be triangles or quadrilaterals. So let's say I graph 4 inequalities, I should say, because there are 4 lines on this particular graph. And the shadings overlap inside the figure. The shading, that's called the feasible region. There are 4 constraints here. Let's say I graphed x is greater than 2, greater than or equal to 2. Let's say that I graphed y is less than or equal to 6. Let's say that I graphed y is greater than or equal to 3. And then let's say this last line is the graph of x plus y is less than or equal to 10. I didn't show you the whole graph, but let's say that's what it is. This region here, that's some sort of quadrilateral, is called our feasible region. The vertices of that feasible region are going to be the values that I plug into my objective function. There is a theorem that we learn about in pre-calculus that tells us that the maximum or minimum has to occur at one of those vertices. So we're going to be looking for those when we graph our inequalities. Let's do an example where we graph inequalities, look for the vertices, and determine what the maximum or minimum is based off of the objective function. In problem 1, we're going to graph these 4 inequalities. They're the constraints: x plus 2y less than or equal to 5, x minus y less than or equal to 2, x is greater than or equal to 0, and y is greater than or equal to 0. Then we're going to find the vertices of our feasible region. Once we find our shaded region, it'll be a polygon. We want to find the vertices, the corners of that figure. We're going to take those ordered pairs and we're going to plug them into the objective function to find out which one maximizes the function. In other words, which one gives me the biggest value. I'm going to tell you something about these 2 particular constraints. They're very important. They restrict you to quadrant 1. When x is greater than or equal to 0 and y is greater than or equal to 0, that automatically means you are working in quadrant 1. So now this inequality is going to be y is less than or equal to negative 1/2 x plus 5/2. Well, how am I going to graph that? Well, probably the easiest way to do it is to plug it into your calculator. After I plug it into my calculator, I would go to the table and determine integer ordered pairs to graph. So I could graph, on my calculator, I see -3, 4 is a point on the graph, -1, 3, 1, 2, 3, 1. Let's see, I'm going to go down here and I see 5, 0. So that is one of my lines. And this graph gets shaded below because of the inequality less than. Remember, I'm restricted to inside of here because of x is greater than or equal to 0 and y is greater than or equal to 0. The second inequality is going to be y is greater than or equal to, see that minus in front of the y, it switches the sign, 1x, minus 2. Let me double check that. Y is going to equal, no, y is greater than or equal to x minus 2, yes. The y-intercept is at -2 and the slope is 1. So the line is going to look like this. And since the inequality symbol changed to greater than, it gets shaded above. That means that this is my feasible region. It's a quadrilateral. It has 4 sides. The next thing that I want to do is I want to find the ordered pairs of the vertices. Some of the ordered pairs are really easy to find. Let me move this up. This is 0, 0. This ordered pair here is 2, 0. This ordered pair here is 3, 1. And don't get fancy with this one. This one is 0, 2.5. What I'm going to do is I'm going to plug each of those into the objective function to find out which one gives me my maximum. So 2 times 0 plus 0 is 0. Well, I'm pretty sure that's not going to give me the maximum. The second one, 2 times 2 plus 0 is 4. The next one, 3 times 3 plus 1 is 10. And the last one, 2 times 0 plus 2.5 is just 2.5. Well, it turns out that 3, 1 gives me my maximum value of the objective function. And that's all we have to do right now. In the next section, we're actually going to talk about a real-world problem where we have to write our own inequalities and then graph them, find the vertices, find the objective function, plug them in, and find out which one is going to give us a maximum profit.